Hi folks, so as requested, this is going to be a quick summary of the hand rules that we've gone over in the electromagnetism topic. I know a couple of people, well I don't know how many people, a few people were off during the, was it the motor effect lesson, because of the art exam. So we'll just summarise this and just put them all into one spot. It's going to be useful for everyone, even if you were there for the motor effect lesson. It's going to be a good idea to have them all in one place, so you could just go over them basically. Right, so let's jump into it. This should be a dead quick one as well, by the way, because it's I'm not teaching it for you the first time. We're just going over it. So first of all, there's a couple of images up there, but let's just talk about what electromagnetism is. Okay, so first of all, an electrical current will generate a magnetic field. We've looked at this in a few different ways, but there's an image there of a coil of wire, so a solenoid, and it's being attached to a battery. So there's a current passing through that wire, and you can see that as the current's passing through it, some red lines appear. So whilst there's a current passing through a wire, it generates a magnetic field, and that's what's happening here. So you can see on this, but when it's not connected, there's no magnetic field. When it is connected, there is a magnetic field, and you can see the magnetic field looks a bit like a bar magnet. It's being generated from one end and going all the way around, and then going back in at the other end. So that is an electrical current generating a magnetic field. Okay, let's move on. A magnetic field will generate an electric current. So this comes from the generator effect, and we've done this in lesson, so the generator effect lesson that we did. And you can see that in this image on the right hand side here. So you can see we've got a coil of wire, that's what this red part is, and we've got that attached to a voltmeter. And you can see that as the person places the magnet, which obviously has its own magnetic field around it, you can't see the field, but it's there. As they place the magnet near the coil of wire, you can see that the arrow on the voltmeter changes direction. It goes one way, and then it goes the other. And it's doing that because there's an interaction between the magnetic field of the magnet and the electrons that are sat inside the wire. The electrons in the wire are feeling a force due to the magnetic field around this magnet. So we can actually generate a potential difference, or generate a current inside that wire. It's called being induced. We call that induced current. And that's what we call the generator effect. So what's that got to do with electromagnetism then? Well, if an electrical current generates a magnetic field, and a magnetic field can generate an electric current, you can see that those two things are linked, hence the term electromagnetism. Okay, so that's why we're using that word. An electromagnet, for example, uses electricity to produce a magnetic field, and you can turn it on and off because electricity and magnetism are linked. So let's go through the 4 hand rules that you need to know then for your assessments. So first of all, we've got the right hand grip rule. So in teaching order, this was literally the first one that I showed you. So what do you need to know then? Well, you place your hand like this. So thumbs up, and your fingers represent one thing and your thumb represents another. And if you look at the diagram, you can see here that your thumb represents the direction of the current. So if I've got a straight piece of wire, so this says the right hand rule, the right hand grip rule, sorry, is used for a straight conductor, for example, a piece of wire. So I've got a piece of wire here. So you can see that this green line here with an arrow on it is a wire. The arrow at the top here is showing you the direction of the current. And what you're meant to do with the right hand grip rule is line your thumb up, because it says there the thumb lines up with the direction of the current. Line your thumb up with the way that the current's going. In this case, it's going up. And the direction that your fingers would curl round is the direction that the magnetic field takes. So you can see that this person's fingers are curling round like this. And because of that, the magnetic field is going round like that. Not because of that, sorry, it's not the fingers that are doing it, but the magnetic field is going round in the same direction that the fingers are. Okay, so we can use the right hand grip rule then to determine the direction of magnetic field around a current carrying wire. Bear in mind, they might ask you to do the opposite of this. They might go, oh, the magnetic field's going around this way. What way's the current going? In which case, you just line your fingers up with a magnetic field, and your thumb will then show the direction of the current. So have a look at this on the right hand side then. I've got this one here, sorry. On the right hand side, I've got an example, just a quick question I want you to have a look at. I've put this on the side because I think I've turned it like that, because I think all the ones that I've shown you so far have been vertical, and the current's either been going up or down. It doesn't have to be. I mean, the direction that the wire's going in is irrelevant. It's the direction that the current is going in that matters. So I'll pause this for a second, have a look at it. Use your right hand grip rule. Which way is the magnetic field going in this image? So pause it, have a quick think about it. Line your thumb up with the current. Which way your fingers curling round? Okay, let's go through the answers to this. So you should have got this. Why have you got that? Well, let's have a look at it. If I line my thumb up with it, it's going that way. And if my thumb's going that way, my fingers would curl round like that. So you can see my fingers are curling around like that. They're curling around like that. So because of that, the magnetic field is also going in that direction. Okay, it's showing you which way the magnetic field is going, and that is for a straight conductor, or they might call it a current carrying wire, or a current carrying conductor. There's loads of words they can use, but they're all talking about the same thing. Okay, so that is the right hand grip rule. That's the first thing that we looked at, and we've done that. Okay, so let's move on to the next one then. So this is the second right hand grip rule, and we're still using our hand in a similar fashion, but now your thumb and your fingers represent something different. Okay, so before my thumb was representing the current, but now my thumb is representing the magnetic field. Okay, so the thumb is going to represent the magnetic field. Your fingers are going to represent the current. So this is specifically used for solenoids. And remember, a solenoid is just a coiled piece of wire. If I gave you a piece of wire that just looked like that, a straight piece of wire, and you literally just wrapped it around your finger, you've not changed what the wire is made out of, you've not changed its thickness, nothing like that. If you just took that piece of wire and just wrapped it around your finger, you've just made a solenoid. Okay, so if I took this piece of wire and literally just did this, perfect, you've just made a solenoid. Now, the first rule that we've just looked at obviously won't apply to this because, well, the wire's not straight. So what do we need to do here? Well, we need to change things up a little bit. If you line your fingers up with the current, then your thumb will point to the north pole of the magnetic field generated by that solenoid. Okay, so bearing that in mind, I've got a solenoid for you there. I've flipped this upside down. So the image on Google where I've nicked this from, it was the other way around. I've flipped it that way. You can see that the current is going in that direction, and you can see that the current's coming out in that direction. So line your fingers up with the current. Which way is your thumb pointing? That's going to be north. So have a quick look at that. Pause it. Have a look at it. Which way would be north? Which way would be south? Have a look at it. Okay, let's go through the answers for this then. Well, the way you want you to look at this is I want you to go, right, well, if the current's coming in there, then it's going up on that side, and it's going down on that side, and it's going up on that side, and it's going down on that side, and it's doing the same thing all the way along. Up on that side, down on that side. So I want you to line your fingers up. Think about if it's curling up on that side, I want my fingers to curl up on that side. So I want my fingers to curl around like that. My fingers are curling around like that. So if my fingers are curling around like that, which way is my thumb pointing? It's pointing in that direction. So that then must be the north end, and that end must be the south end. Let's have a look. Perfect. This end is the north end, because when my fingers curl around like that, my thumb was pointing north. And if that end's north, then, well, by elimination, that end must be south, okay? And remember, the magnetic field of this, I'll just draw this just simply here. The magnetic field looks very similar to a bar magnet's magnetic field. When I say this is north and this is south, I mean it literally has poles, and the magnetic field looks very similar to that of a bar magnet. Meaning that if this is the north end, then bloody pen, then the magnetic field line comes out like that, around and back in, and these actually meet like that. But there's loads of magnetic field lines, isn't there? Remember that magnetic flux density diagram I showed you? There was magnetic field lines everywhere, wasn't there? Okay, so and then there'd be another one there, and there'd be another there. Notice I'm always drawing it in the same direction. Why am I always going that way first? Or it might be that way on your screen. Why am I always going that way first? Because it goes from north to south, so it's coming out of this end, out of this end, out of this end, out of this end like that, and then it's going around, and then it's coming back in on the other side, so it's going in there, in there, in there, and in there. Okay, so that is showing you the second right hand grip rule is linking current direction to magnetic field direction for a solenoid. Okay, so that's that one. If you're not too sure on that, give it a Google, watch a free science video or something like that, or go on Bite Size, see if you can fill those blanks in there. Obviously, we've still got time in school, so you can ask me about it as well if you need a bit of extra support. Right, the left-hand rule then. So the left-hand rule, this is where people start to get things mixed up, I think, because we're adding in a third variable. For the first two, there was only two variables on each hand. So current and magnetic field. For this one, it was current and magnetic field. Now I'm telling you that there's motion involved as well. Okay, in fact, it might be worth pausing for a second to explain why there is motion. And I know I keep bringing it back to this, but I want you to understand two magnets near each other will create a force. Okay, so dead simply, a magnet there and a magnet there. If one end's north and that end's south, there will be a force of attraction. Their magnetic fields create a force of attraction. If I recreated this scenario again, but but this end was north and this end was south, there would still be a force produced, but it's no longer attraction, now it's repulsion. So you inherently know that magnetic fields, when they interact with each other, can produce forces. And that could be a force of attraction or repulsion. Depends on the poles of the magnetic field. As soon as you know that, and you know that currents can produce magnetic fields, this should all kind of fall into place. Okay, so the left-hand rule then is used to determine motion from current and field. So we're using two of these variables, current and field, to determine motion. That being said, they could ask you to use the left-hand rule to figure out either current direction or field direction. It doesn't matter what they're asking you for. As long as you know the direction that your finger should be pointing, you can figure out any one of these using the other two. Because as soon as you get two lined up, the third one is automatically lined up with the direction that it needs to go in. Okay, so looking at this then, the left-hand rule, the thumb represents the movement they've got here, because thumb's got an M in it and movement's got an M in it. But the way I taught you is thumb starts with a TH and thrust starts with a TH. It's the same thing, isn't it? Okay, your forefinger points in the direction of the field from north to south, and your second finger has a C in it, so that represents the direction of the current, going from positive to negative. Remember, that's conventional current. So practice that. Practice going. Get your finger guns out, stick your middle finger out at a right angle, okay? So you can see the direction that each of these should be pointing in, they're linked. I want you to use this now, and it's probably going to take some rotation. Look at the example on the right-hand side, the task. Which direction will that wire move in? So pause it, look at it. Which direction will the wire move in? Okay, you're given current, you know which way fields go. Which direction will the wire move? Pause it and have a quick look. Okay, let's go through the answer to that then. So the first thing I'm going to do is I'm going to draw the magnetic field on, and know that magnetic field goes from north to south. I'm going to draw the current on, and I know current is being given from positive to negative here, so the current's going down. And then I'm going to get my hand out and I'm going to go, right, what am I going to line up first? I always go for field first. I don't know why. It doesn't matter. So I'm going to point my finger from north to south. North to south. I might be pointing the wrong way according to you, but on my screen this looks right. So it's pointing from north to south. Okay, what next? Well, my middle finger, I need to now line up with the current. I've been told the current's going down, so point my finger down. Okay, is my first finger still pointing in the direction of the field? Yeah, it's going from north to south. Okay, is my second finger pointing in the direction the current's going? Yeah, the current's going down, my finger's pointing down. Okay, oh, my thumb's pointing at me, like it's coming out of the screen, which means that this wire would experience a force and would move in that direction, out of the screen. Okay, and I've said this in lesson a few times now. I know it kind of looks off, and like, how do I draw it showing it's coming out of the screen? There'll be a margin of error within the mark scheme that allows, like, if you've done that, or straight out like that, they know what you're getting at, okay? They know the direction. I mean, the only other way you could have got it wrong, realistically, is if you'd have gone, oh, it's going into there. There's a big difference there. The examiner's going to know, okay? So these guys here at the top that I've just done are incorrect, but any that I've drawn at the bottom there would be acceptable, okay? If that's not making sense, again, go and watch a free science lessons video, give it a Google, try a couple of like Seneca or Century Tech. There's some information on there. I need to speak to you about that later, but you could have a look at those. Okay, coming on to the last one then. We did this very recently. This is the last lesson that I taught you in the P7 topic before we started the space topic. So let's have a quick look at the next one. The right-hand rule. And you might be thinking, we've done the right-hand rule. We've done the right-hand grip rule, and we did the second right-hand grip rule. This is just the right-hand rule. And remember, the left-hand rule looks like that. Well, guess what? The right-hand rule is just its mirror opposite, okay? So your right-hand rule looks like this. Why are we using the right-hand rule? Well, the left-hand rule is designed for looking at motion when motors are involved. The right-hand rule is designed to look at current direction when generators are involved. Okay, so it's used to determine current direction from field direction and motion direction. Look at that. I've been given two of the three variables again. It's like an equation, isn't it? You know what I mean? Speed equals distance divided by time. If you know what the distance and the time, you can calculate the speed. It's the same thing with this. If you know two of the things, you can figure out the third using your hand rule, okay? I've put, for example, in a generator there, and I've put this, generator. Remember, generator, as in you've got to use your right hand if it's a generator. How will you know if it's a generator? Are you being asked for current? Then it's a generator. You're very likely being asked for a generator, okay? So let's have a look at this then. We've got the thumb representing movement again. You know this. So thumb's got an M in it. Movement starts with an M. The first finger is pointing for the magnetic field from north to south. Again, same as the left-hand rule, no different there. And then the second finger, second's got a C in it, current starts with a C, so your middle finger is going to represent the direction that the current is going in. So here's an example then. Look at this. This is like a really, really basic generator. I've got a wire there. So I've got a wire. Notice how the current is not labelled. We don't know the current. Don't look at this and go, oh, red's positive and then the blue then must be negative. So the current's got no. Ignore that. Okay. In fact, on an exam paper, they won't even have colours. Okay. So the colour is irrelevant there. Don't look at the colours to determine current direction. I want you to use your right hand rule. Okay. So you've been given the movement and you know what the magnetic field is. Use your right hand rule now, which is that one there, to determine the direction of the current. Okay, where should you draw it? Doesn't matter. On the wire somewhere, an arrow showing which direction the current's going in. So pause it for a second, have a quick look at that. Okay, here we go. So using my right hand rule then, so I've got my right hand out just like I would do if I was using my left hand, pop it out like that. And I'm going to match these things up now. What am I being asked for? Current. Well, that's my middle finger. So I know I can't line that up with anything just yet. I've got to get these two right first. Okay, so my first thing I'm going to do is I'm going to, like I say, I always go for the field first. It makes no difference, but I do. So my first finger is pointing in the direction of the field from north to south. Okay, I've got that lined up. Right, I've got my thumb pointing up in the air, and would you look at that? The movement of the wire is being moved up. Sorry, the movement of the wire is up anyway. So the person doing this has moved the wire up through the magnetic field, and my thumb's pointing up, so that's already aligned. That's already aligned. So thumb's pointing up, first finger's pointing in the direction of the field. Which way is my finger pointing? That way. My finger's pointing that way. And if I look at it, I mean this direction. So I'm going to put an arrow on the wire like that. But you could have put it there, that means the same thing. You could have put it there, it means the same thing. It's irrelevant. As long as it's on the wire and it's pointing in the direction that the wire the current would have moved in, you've just got yourself however many marks that is on a mark scheme, on an assessment, sorry. Right, hopefully that makes sense. That's all 4 hand rules in how long was that? 10 minutes? I don't know. What I want you to do now is I want you to have a look at this. It's a quick worksheet. I'm just going to give you the answers to this in a minute, but pause it and try it. And I want you to try these questions. It's linking electricity and magnetism. Okay, it's kind of trying to bring all of that together. So pause the video, try those questions, and I'll give you the answers in a second. Okay, I hope you're ready for answers then. So I'm not going to go through all these because, well, you've seen the questions, you've tried the questions, so boom, there's the answers. It's split up into 2 activities because it's got electricity, magnetism, and the motor effect at the top, and then it's got motors and generators at the bottom. So those are the answers. Give those a mark. What did you get? Is there anything that you didn't get right? Is there a reason you didn't get it right? Is it a silly mistake? If it was a silly mistake, then maybe just a quick refresher and move on. If it's something you genuinely still don't understand, then we need to do something about that. We need to plug those gaps. We can't just move on and go, oh, it's fine, I don't know it. It's not fine that you don't know it. You need to know it, okay? So you've got a few choices there. You could go onto BBC Bite Size. You could have a look at that. You could check out a revision guide. You could have a look at that. You could try Seneca. There's some information on there. There's some stuff on there that you can find. I would suggest Century Tech. But I went on there before and there wasn't much in terms of generators. So if the thing that you're getting stuck on isn't generators, but it's like electromagnetism or electromagnets, the motor effect, there's some stuff for that on there. Remember, it's just Century Tech on Google, and when you go to sign in, click on sign in with Google. Don't sign in automatically with your account from school. You've got to click sign in with Google first, and then you've got to find that stuff yourself on there. I did try and assign some stuff for you, but there's no classes on there at the minute. I don't know why. I think that's getting sorted soon. So there's the answers to those. Right, what's next then? I found a BBC bite-sized quiz. There's the link there. I know you can't click on that, but you could type that in. It's not a massive address, is it? So that is just a quick, I think it was 10 questions based on the P7 electromagnetism topic. You could try that, and again, it'll give you some ideas what you're good at and what you're not good at. I'm going to put the end of topic assessment on Google Classroom with this assignment. I'll put the mark scheme up there as well, so you can try that. Another way of figuring out what you know and what you don't know. We've got 8 lessons in school, is it? 6 lessons in school left? I'm not too sure. We've not got many. We've not got enough. I'll put it that way. So if you've got anything that you still want a bit of help with, make a note of it, bring it in school, email it me. It doesn't matter. And obviously I can try and plug those gaps for you. But hopefully that was useful. If you've got any questions, either drop them on the YouTube video or put them on Google Classroom and I'll answer you on there. Okay, see you later.